Okay, thank you for your persistence and staying here. And also I would like to thank for the organizers for this fascinating workshop. Up to now, it is very interesting and mind-provoking. My talk will be about gradient expansion, actually. And the main question will be whether and how gradient expansion is commutative with the second law exploitation. And my talk will be completely non-relativistic. More properly, it will be Galilean relativistic sometimes. So, and my ambition is to extend a little bit what we consider as a fluid. And you will see why. And there will be three important aspects. First of all, how we use the entropy inequality in classical fluids, and about the Galilean relativity, I mean whether and how things are covariant in the non-relativistic physics. And again, the final aspect is extensivity. Those are some fine points that are important for the possible extension to at least special relativistic space-time. First of all, about fluid instabilities. We know several fluid-related instabilities. For example, the Lorentz-Abraham-Dirac one, the Jeans instability related to gravity, the Boboliev instability mentioned already, the Eckard instability appeared almost in every talk, turbulence, and one maybe not well known, but the Korteweg instability, which is the instability of gradient expansion in fluids. That goes back to van der Waals. Van der Waals was who won the Nobel Prize because of surface tension, actually, and introduced the gradient of density as a thermodynamic variable. And Korteweg was his student. And what he wanted is, so the Korteweg fluids are the attempt of Korteweg to generalize van der Waals' ideas for dynamic case. It was a long time ago. And you see, essentially, the Korteweg fluids are based on these. So Korteweg established the most general isotropic pressure that depends on the gradient and the second derivatives of the density as well. And there is a quadratic term, but it is an exception. By the way, the notation will be strictly following that way. So nabla is the gradient or the divergence if there is a dot. And I will use this kind of invariant non-relativistic notation almost till the end of the presentation. Anyway, what Korteweg suggested that, okay, let's say this constitutive equation for the pressure, and maybe we can describe the bubbles growing and the dynamics of them. Alpha, beta, gamma, delta are density-dependent material parameters. However, it is unstable. It was not very apparent because it was before the computer, so solving this equation is not so easy without them. And also, after Eckard established the entropy balance-based exploitation of the second law, still it was not easy to deal with that kind of gradient expanded fluids. And one important result was due to Dunne and Sherin still before the computer era, who applied the thermodynamic second law analysis for these so-called weakly non-local fluids. And it then actually established the relation between, they established that alpha, beta, gamma, delta cannot be arbitrary. They should be related somehow, and then it is a stable thing. Second point is, it goes back to Madalung, also a long time ago, because not, I think, some months after Schrödinger has written the Schrödinger equation, Madalung introduced this kind of polar decomposition to amplitude and phase decomposition. And the Schrödinger equation was transformed into this form. This is the imaginary part, this is the real part. This is very well known, I think, since that. And what is interesting that this, you can see that this is the continuity equation, and that is the so-called Bernoulli equation, because, or if, we introduce the velocity potential, so we consider a potential flow without vortices, And then this is the energy balance, actually. Taking the gradient of the energy balance, we get the momentum balance in this very interesting form where you can observe this particular potential, which is called Bohm potential. After that was discovered by Bohm, which is a rho and gradient rho and the second derivative of, depends on the second derivative of rho as well. And interestingly, if we put, the gradient of U multiplied by rho is actually a divergence of a pressure, still constitutive one, a Korteweg pressure, you see, because this depends on the gradients and the second gradient. And then we obtain a complete hydrodynamic analogy of quantum mechanics for a simple Schrödinger system. Of course, this is somehow mysterious. Of course, the Bohm potential, you know, if you know, this is very much discussed whether is it really quantum mechanics or not. However, it is important to know that it is to transform Schrödinger-like equation to fluid form is or basics of understanding quantum fluids. However, the mystery is that why potential for why this Bohm potential and actually how this pressure emerged and whether is it important or not. Because you see, this is a normal, how to say, Newton-like equation in a particular potential, which potential depends on rho, and the continuity equation is somehow connected to the continuum. So it's a very particular form representing the propagation of a particle. Okay. And as was that was the invention of Madelung, or it's inside, that's the velocity potential. The gradient of S is the velocity. Let me, but just no. I'm sorry, it stopped working, so I cannot go back. So something happened. Anyway, that's sorry. Now, anyway, I continue and we can go back, but so different there. Okay, no, it is okay. So, may I? Just a moment. Okay, so a question again? Oh, now what? I have to click somewhere, yeah, and then back, and then, okay. S is here. He realized that it's a Bernoulli kind of equation if you introduce a velocity potential. Yes, sorry, yes, so sorry, I have forgotten to correct. This is S, the phi is S here, so that was a, that should be, sorry, thank you very much, Gabriel. So, and maybe you know the works of Wolowik, who actually the prophet of this fluid, quantum fluids, and there are many quantum fluid correspondence and that appears in various parts of physics. This is a truncated version, you see. And also in heavy ion physics, Kodama and Koide suggested that kind of version in a stochastic presentation. Stochastic is not really different in this sense. And my third point is that actually in case of normal continua like this table, rheology is the art of the flow. So actually those materials that we think solid are flowing mostly. The famous example is this tar drop, which is really in every 25 years drops one. So this is really like solid, but rocks are flowing as well. So this is a technological question. ASR means anelastic strain recovery. This is a kind of technology in rock mechanics using that rocks are flowing. And the method of modeling that kind of behavior is to introduce so-called internal variables. Internal variables are extra fields describing structural changes in the material. And of course, we don't have kinetic theory. Therefore, the evolution equation is constructed mostly by the second law, which is also useful when we have kinetic theory. Of course, in case of non-relativistic gases, we have the same moment series expansion technology. However, as well as in case of relativistic theories, we definitely or sometimes need to fit the parameters, not because they cannot be calculated, or the gas is not so idle. Therefore, the kinetic theory parameters are sometimes fitted. And sometimes they are not unexpectedly. The structure of the equations is not really that we follow from kinetic theory. For example, in this figure, it turns out that the so-called Guyer-Krumhans equation, which is a different kind of truncation than the Katanow equation. Katanow is the Israel Steward part of, Israel Steward-like version for heat conduction. So anyway, this Guyer-Krumhans equation is very well behaving for describing a heat conduction if metal foams. No phonons, nothing, just structure, different structure. So what my point is that the evolution equations are sometimes can be constructed and actually obtained by thermodynamics. Of course, kinetic theory is helpful. Guyer-Krumhans is actually a kinetic theory. This is a linearized Boltzmann equation where Guyer and Krumhans invented it for description of second sound and ballistic propagation. Okay, now how this kind of second law-based construction is working and what are we doing here? First of all, let's say a simple fluid, balance of mass, momentum, and energy, total energy, and an additional scalar field with undetermined evolution equation. And in this case, our thermodynamic state variables usually, this is, by the way, mass-specific quantity, this A, so it's not density, but it's not really important here. So those are the variables of the entropy density. And what we like to do is to solve the entropy inequality, which assume to be valid under the assumption that the balances are valid. So all along the solutions, it should be valid. And the constitutive functions are P, G, J, F, and S. S is somehow distinguished. And the main point is here to fix the so-called constitutive state space. Let us fix it in that way. Constitutive state space that all these variables are depending on this introduced E, rho, and phi, and the gradients, and especially the second gradients are important here. And if there are several techniques to do that. Mostly they based on let's say this is a constrained inequality. The best thing is using some kind of Lagrange multipliers in case of inequalities, especially in case of differential inequalities, they called Lagrange Farkas multipliers. And then they give constraints how the various constitutive functions should look like. And the essential way, it is not very complicated, very straightforward, but can be time consuming. Yeah. That is substantial time derivative, co-moving time derivative. That's somehow convenient, but you can do it with partial time derivatives as well, sorry. So V dot equals dt V plus V times gradient V. That's actually, that's a 4-dimensional thing, and that I will go back there. But co-moving time derivative simply. And the essential part of the technology is that along the differential equations, the coefficients, in the inequality, the coefficients of this so-called higher order derivatives, which is called process direction space, should be 0. And then, if you believe me that it works, and I introduce a convenient simplification. I separate all that kind of extraordinary things into an energy density, which I call perfect energy. We will see why. It will be convenient. Then this is a kind of internal energy or fluid internal energy. Then our formulas will be simpler, and this is the entropy production density rate that we got. Of course, you may use Gibbs relation and some kind of normal thermodynamic notation works. you need to pay attention that those are all specific, mass-specific quantities. That's why pressure and not the chemical potential is here. And what you got, this is the thermal part, proportional to the gradient of the reciprocal temperature. That's the normal heat flux. And some additional terms. And also the mechanical part, where you can recognize that this is Euler fluid if the P in the momentum balance equals the thermostatic pressure multiplied by the unit tensor, then we get Euler fluids and several additional terms depending on the gradients. Therefore, the concept of dissipation, what is dissipative, is extended in the sense that all fluids that where the P equal this pressure of the perfect Korteweg fluid, or even more general, it should be considered as idle or non-dissipative because this part is zero. And also you may observe the third term related to F. So this is a restriction for the possible evolution equation of the phi field. If it is non-dissipative, the evolution, then we observe a kind of variational derivative there, an Euler-Lagrange form. No Euler-Lagrange, no variational principles were used, only the second law. Okay, what kind of properties can we conclude yet? So as I mentioned, the ideal field equation is variational, and the ideal pressure has this form. Somehow it's out of the picture, sorry, but I think only the closure parenthesis is missing. It doesn't seem to be very intuitive. However, it has it's an important simple property, but which I call this is classically holographic, in the sense that the divergence of this perfect pressure can be written as rho times the gradient of a potential. So this is not a space-time equality. This is a constitutive equality. So if I know the pressure, I can calculate phi. So all thermodynamically compatible fluids that fulfill the second law, I mean, perfect fluids will have this property. So the bulk forces can be substituted by surface traction, the surface forces. This is interesting because if you substitute here, I mean, into the momentum balance, we get this Newtonian-like form that we observed in case of quantum mechanics. Actually, in this case, they are conditions. So we need to introduce homothermal, I mean, homogeneous temperature, and also ideal field equation, so without dissipation. So this is, but those are interesting conditions. So this is the end. Finally, we may recognize that it's also a constitutive derivative, variational derivative, surprisingly. Okay, let's see an example. It means that in this construction, everything is originated in this perfect energy. If I introduce this energy form, you may recognize here the usual gravitational field energy. And actually, this is also a gravitational field energy, but usual form, but that's another point. Then we can deduce simply that the perfect pressure has this form, the potential has this form. You see the chemical potential and the simple gravitational potentials. Whose gradient multiplied by rho is the bulk force that's more or less known in case of gravity, and the field equation also emerges. And you see that the momentum equation is somehow connected to this. No, phi can be an external field. It doesn't depend on rho. Therefore, this is really a interesting form of the gravitational field propagation. I mean, the momentum of the gravitational field propagation. Let's see another example. Again, let's see this epsilon has this form. Again, quadratic, but undetermined coefficients. And then we can calculate that this is a particular Korteweg fluid where the coefficients are restricted. Everything is, every coefficient is generated from this generator in a non-trivial way. And of course, the corresponding, let's say, hollow potential or whatever can be calculated. And we have these and if B1 is K over rho, then we obtain the Bohm potential. So this is a particular form of the Bohm potential. And you see, this is, by the way, just the after some transformation, we get the Bohm potential and the fluid chemical potential as well. It is interesting to see that if of course, if the fluid pressure or the fluid chemical potential is 0, then we can try to find, or also with that, a complex field representation. What are the conditions of a complex field representation from this fluid mechanical point of view, reversing the way of thinking of Madelung? Simply, first of all, assume, or let's say we have deduced this holographic property. Therefore, we have the previously mentioned pressure, force, or potential transition. So those are the momentum balance and the mass balance. And actually, the vorticity is almost constant. More properly, this equation is valid, but this is a particular co-moving derivative of the vorticity. This is it's called upper convective derivative. So if vorticity is 0, of course, there is a velocity potential, S exists velocity potential, and this is not so strict additional conditions, almost potential flow what we have, just the vortices are conserved and somehow they are, let's say, deforming from the external observer point of view. And as we see, we can try to find a complex field representation. By the way, here, this should be an imaginary. So try to find F1 and F2 and put together everything. We obtain, without any condition, this complex field equation should be valid. It means that if I choose particularly or potential that it will be minus the Bohm potential, this is the Bohm potential with the minus sign, then we got linear equation for that, which is the, not of course choosing S0. S0 was introduced here. So this properly with the, so Planck constant and the mass, then we got Schrödinger equation, but it's not only, this is the quantum fluid equation in general have this form. If the Bohm potential is introduced are that way. Okay. Maybe this is a little bit extension how the second law of thermodynamics works in case of non-relativistic physics. However, there are several pitfalls in this thing. One of the pitfalls is how the equations are not covariant. Not covariant in the sense that relative quantities, relative velocity, everything is relative. Therefore, it's interesting to see it from a space-time point of view. So let's introduce a very simple Galilean relativistic space-time, which is a 4-dimensional flat manifold. Let it be a vector space, and I introduce absolute time. Therefore, there is a foliation that represented by this projection to a simple affine 1-dimensional flat manifold. That is the simplest and maybe the best representation of non-relativistic space-time, and in generally 4-dimensional. And what is important here is the projection. So there is no metric structure on space-time, only on the foliations, only, and therefore there is no relation to connect vectors and covectors as different parts of the linear structure. Anyway, this is the detailed description of the manifold, and you see only on the instantaneous space, 3-dimensional spaces, I introduce an Euclidean structure. That's the minimal representation. There are some fine points, for example, This should be an affine space. In principle, with vector spaces, I will use indices, but those indices do not relate foliation. Just for those are abstract indices in the following. Yeah. Because let me show. Because this is a 4-dimensional, and actually, the Galilean. So the Galilean transformation of vectors, 4 vectors and covectors are consequences of the structure. So space and it's this transformation. So this is the property of due to the absolute time doesn't transform. However, yeah, and all vectors transform like space-time vectors, and all covector transforms that the time-like part, the scalar part, changes and not the space-like part. And it is important because all derivatives are covectors. Therefore, for derivatives, for gradients are absolute, do not transform at all. But we should take care of the time-like part. And this is well represented, for example, that the balances can be written. I mean, of course, those are covariant and more properly invariant, and can be written in different forms, just transforming them with, let's say, denoting them, let's say, material related or laboratory frames. We can observe and transform them into this substantial form. Substantial, this is called in this literature that substantial balance is the co-moving balances expressed by the laboratory frame splitted quantities. Anyway, what I wanted to emphasize that these are invariant, and one may look at the, for example, the substantial time derivative as covector transformation. One may look for the convective separation of current densities as a particular vector transformation from the co-moving to the laboratory phase. But, and now, the question is, what is energy? Energy, where the energy is the question. The kinetic energy is a quadratic expression. Therefore, if I would like to represent it, kinetic energy density, quadratically depend on the velocity, if I want a kind of covariant energy, then I realize that this should be a part of a second order tensor. So if I would like the energy momentum balance non-relativistically, I mean, this energy momentum density tensor non-relativistically, it's not enough to introduce a second order tensor because I need a second order part for the density. I need a third order tensor. That if I accept, and if you accept, then one can introduce a third order tensor, mass energy momentum density flux tensor. The density part looks like that, the flux part looks like that, and where the time-like part is rho, the space-like part is the energy density, which is second order tensor. It looks like strange. However, if you think to non-relativistic kinetic theory, this is what we do there, actually representing somehow energy in this way. And you may accept it is okay. And please look at the transformation rules of the different quantities. So I have, okay, density doesn't change, momentum, that is a space-like, no, the indexes denote the space-like parts, momentum changes like a vector, energy density changes in this way. This is the kinetic energy as it should. And of course, the flux, I mean, diffusion flux changes this way. And very interesting is the transformation rule, for example, the heat flux, the energy flux, which is quite complicated, but completely corresponds to the transformation rule that you get in a very different and more complicated way from kinetic theory, where introducing divergence type higher order theories of Ruggeri, Müller, Liu kind, you need to consider the the Euclidean absolute forms in addition to the main field. By the way, then Galilean, so the transformation of energy rule will be transitive. So different observers looking, the third one, just it is not like relativistic, which is not transitive. But jumping to the balanced equations, you see this is the divergence of the third order tensor. And just using the previously introduced splitting, so this is nothing, time-like part, space-like part, and introducing these nominations of energy density, momentum density. And what is maybe interesting to observe, this is the rest frame form, and this is the laboratory frame form, and the red terms are related to the momentum density, which does not move together with the fluids. Therefore, rho times u, I mean the rho times v, is not the momentum automatically. Otherwise, in the rest frame, it would be 0. And of course, if I take it 0, so if I fix the frame, again, in a non-relativistic case, also there is a discussion about which is the right frame. You may look at the works of Howard Brenner, who argues that the different velocities in the Navier-Stokes and other equations may be not the same, so it goes back to that question. But anyway, this is the full form, and somehow we neglect the local momentum. We fix the frame, the mass, and the momentum at the same times. By the way, just times v dot is actually the part of a transformation rule in this point of view. So this is a quite, let's say, maybe mind-provoking view of non-relativistic fluids, especially comparing with the relativistic ones. There are less differences than one would expect, I would say. And I don't continue, but my final remark that, of course, in this, for this simpler fluid, one can introduce the entropy balance, and the entropy balance will be invariant. And normally the entropy balance is not invariant. This is the so-called Prigogine paradox. So just transform Galilean transformation entropy balance because of the relative velocities inside, especially the mechanical work is not invariant. If we introduce in this way with some additional, but there will be there is no necessary to have. Yes, of course, this is the diffusion flux. This is, I mean, the non-comoving, that's a conductive current density of the mass, which is the self-diffusion in this one component fluid. Of course, it is not one component fluid, then you can imagine in one component fluid, it's a question how you interpret it and what is the role. This is a question that's never appeared. I mean, I never encountered this kind of quantities because we always fix the non-relativistic frame to the mass. No, never. And in this case, if you fix to the mass, those are 0. And also, there are some, let's say, thermodynamic consequences of that. Because naturally, entropy density in the following would depend not only on the so-called static quantities, but also with this co-moving density, and therefore the intensive quantity, the related conjugate, is a velocity kind quantity, like the thermal, like the beta frame in special relativity. Yeah. The Prigogine paradox is that the mechanical part of the entropy production, this one without the gradient terms, so the P minus P static multiply the gradient V, when you transform from laboratory to rest frame, it is not covariant. And this is a problem in chemical technology. Actually, this is a real problem, not very, because it depends how much energy should you use in this kind of flowing systems. Not very big problem because the viscosity is normally does not important. I mean, it cannot be handled. Solution is that you should use the proper balances in 4 dimension. And then you understand how these quantities are. I mean, it is not written here. This is here. Then it turns out to be really invariant, and so this is frame independent. Yeah, yeah. Yes? Yes, in the, you mean this one? This one is the same. Is J? No. This is eliminated. That the conductive part is eliminated. This is sorry. The convective parts are eliminated. This is hidden in the co-moving time derivative. Yeah. So this is this is no flow frame is introduced here. This is a general splitting of the four tensor into different parts. So if I fix somehow, for example, fix J0, then of course this term disappears. Navier-Stokes, usual Navier-Stokes is in the black. Yes, exactly. With the energy balance. And of course, yeah. Another, so I thought, and one need to be aware of these absolute formulas. Otherwise, there is a question whether relative velocity enters in the thermodynamic state space, whether time derivatives enter in the thermodynamic state space. They cannot. They are very problematic. And how the gradients are safe because they're absolute. They do not transform. They really safe from this point of view, and this is the problematic or the problem set of so-called material mean difference, that for material constitutive equations should be independent of the observer also, and especially in non-relativistic case where a lot of or real materials are. And so it's not an academic question, just I wanted to say, but I don't want to go into this direction. So yeah, just one sentence back that, so this space-time awareness results in that I use the proper, let's say, choice of the variables at the end, and I did not consider, for example, the relative velocity, or it was a little bit hidden. And the other pitfall in the gradient expansion when you introduce real thermodynamics is the extensivity. Why? Because, okay, first of all, extensivity in the sense of the first order Euler homogeneity, where we know well that the first order Euler homogeneity of a function is the definition. And this is equivalent, the existence of density with this property. This is zeroth order Euler homogeneous, I mean S. And equivalent, again, with the existence of Gibbs relation, where the y and y to yn are the partial derivatives here. No, it is simply functional. No, differentials are not important. Just it's important that these three properties are equivalent. And why? Because extensivity is a connection. This is a downscaling of our thermodynamic properties. And we are used to use fluids, where this downscaling is not problematic. I mean, small fluid are similar to large fluid. And of course, there are questions behind that. So this should be measures, but we are speaking about extensive quantities in a mathematical sense. So it's kind of properties. And thermodynamic limit is connected to that. However, if we start from below, if I assume that let it be thermodynamic relation, I mean energy, let it introduce a specific entropy or entropy density with some properties that depend on, for example, droplets with non-homogeneous energy dependence. Therefore, they are definitely, this expression not first order Euler homogeneous. I can construct a macroscopic entropy, upscaling, introducing simply the, for example, number of droplets and introducing new thermodynamic variables in this way. So that's, by the way, a trick what used in thermodynamics for small systems or nanosystems, or that's a part of the tricks. And you may understand that, for example, if it starts from a microscopic representation, then what you get is the chemical potential at the result of upscaling. So you need to add, or actually there is a chemical potential is defined in this way when we put the microparticles, I mean particles simply, and put together them. But the point here in case of gradient systems is that gradients are not measured. general, and one need to do some particular, let's say, adjustment to do the gradients. And that goes back again for a long time because people, these internal variable tricks were a long time ago suggested, by the way, first as far as I know, Mandelstam and Leontovich, later on Landau and Lifshitz. You may find in the statistical physics volume of the series, but they fail. They are not good because somehow they don't pay attention. So you cannot introduce arbitrarily internal variables. You need to pay attention to this scaling property. For example, a famous example, when you introduce thermodynamics of elasticity, this is the deformation. A deformation is a gradient of the deformation vector, deformation tensor. And if you don't introduce rho here, I mean dividing the pressure in this is the simply Cauchy pressure, then simply you don't get good formulas. So this is, by the way, specific quantities here. If you go to densities, which is more usual, then you see that the difference is important. So you obtain a Helmholtz free energy term as an addition. So these kind of things are somehow one should pay attention, and better to start from low. I mean, better upscaling instead of downscaling. So some part of thermodynamics, especially in this case with gradients, the thermodynamic equilibrium, as we have seen, at least the ideal gradient system mechanical equilibrium will be not homogeneous. Neither with gravity is not homogeneous, but still thermodynamic equilibrium. And start from local quantities. Of course, your macroscopic bodies, so how to say, the energy will depend on the form of the bodies. Of course, the size will play a role. It's well known, is the self-gravitating fluids of the, how to say, Chandrasekhar, described by the Chandrasekhar equation, for example. That's well-known examples. Anyway, this is another pitfall. One need to pay attention a little bit when going to the macroscopic situation. And I was very fast, sorry. So then I will actually at the end, summary. Fields can be thermodynamic state variables and the gradient of fields as well. And the gradients of thermodynamic previous extensive quantities can be also included in the classical or more or less classical schemes if extensivity in space-time are properly represented. The classical holography, the mentioned property, was an emergent consequence of the second law. It is a general consequence, very surprisingly. Different Euler-Lagrange form equations appeared in the scheme without variational principles, also interesting. And Newtonian gravity, quantum fluids, and the not mentioned various modifications emerged. So actually, what we are looking now and what I'm looking now is that kind of small modifications that could be measurable or detectable, because this gives you really a general scheme, non-relativistically, of course, how to, with several modifications and deviations from the usual equations and evolution equations, especially as you observed, one generator function gave you the ideal field equations and as well as the dissipative field equations. So somehow in one stroke. Of course, question of, I don't know how far can we see in this framework. Questions is universality, what is local equilibrium, how much hydrodynamics is an effective theory if Schrödinger equation is part of the system. And of course, one of the benchmarks, that's stability and how could we produce a more or less stable dynamic. So dynamic and thermodynamic stability, how are they connected? You see the quadratic forms in the gradients, those means the thermodynamic stability is in this sense somehow fulfilled, however, in a functional sense. And of course, in this case, whether one may question whether the second law of thermodynamics is a first principle or what. So This is maybe the most interesting question. And this, okay, I finish here. Thank you for your attention. Maybe if I have some time, I show you. Yes, I show you some interesting. What is the modification of Newtonian gravity that emerges from, which is unexpected, in a sense? So, okay, these are the previous equations. Maybe I did not correct yet. This is the previous energy. By the way, that's a question why this energy, because the usual field energy is minus this term, field energy density, but you get thermodynamically correct things with this one only. And it is because of the holographic property, because the gravitational work density, I mean power, rho times V times gradient phi, can be transferred to pressure. And what is, whether the pressure or the, whether the gravitational energy source term is represented better with the pressure or with the potential is in this case is a question. Anyway, what I wanted to say that, okay, we have these equations now without the gradient density terms. And what you get is, of course, perfect self-gravitating fluid looks like that I've written previously. However, is a possibility now to, okay, to introduce dissipative gravity. Why not? I mean, this is, if F is proportional to the Poisson equation, that's dissipation. And actually, we don't know, okay, we know gravity is not dissipative, definitely, but as the measurements, actually good in this case, only the microsecond scale. I mean, no, we cannot, how to say, if there is a delay in the gravitation, if there is a very small dissipation, so there's a limit what we can measure and what we measure, but it's not the point here. But the point here is that as thermodynamic quantities, let's see, non-dissipatives, so there can be a coupling between the scalar part of the pressure and the scalar gravitational dissipative term. And it is, if it is antisymmetric, that still gives you zero dissipation. Let's see what is the consequence. The consequence is this corrected Poisson equation. The Poisson equation corrected with quadratic term. And this has a very interesting property. It is an exact solution with logarithmic potential. It means that the force field, actually, this is an exact solution for spherical symmetric case. Actually, this is a crossover or whatever. So this is a transition from a force which is proportional to the, inversely proportional to the distance. And in a farther regions, it is inversely proportional to the square of the distance. And this is what we observe in case of dark matter. This is the kind of force field that we seemingly experience if we forget dark matter, which this is what modified gravity theories are looking for. By the way, anybody is familiar with modified gravities like modified Newtonian dynamics, they actually don't have this particular solution, only with some manipulations. Whatever, let's try whether does it work. This seems to be promising. What we have done is just made the proper fitting with one single galaxy. And what I can say that you see, solving the equations with that single galaxy, by the way, it is still, no, it is, yeah, it's not written. But we compared with dark matter, the best dark matter fitting and the best bond fitting, and it is comparable, but which is not a big wonder. What is maybe interesting that it follows a little bit the fluctuations of the density out of the galaxy. By the way, so this is the distance of the galaxy, this is the velocity, and what we use as a source is the measured baryonic density. And if we use Newtonian gravity to calculate the velocity field out of the galaxy, that we could get the red curve, and the green curve is the density of the gas, which is independently measured, and the observed, let's say, brightness. So the baryonic density is calculated from the brightness of the galaxy, and the gas is from the spectral property, and then those put together was used as usual in this business to as a source term of the previous equation here. And then actually it gives you a quite good fitting, but it's not no wonder, as I told you, because yeah. K is the fitting parameter. That's a transport parameter. Which means that the scalar pressure is connected to the field equation. So this comes from the some kind of pressure contribution. It's maybe, as far as I understand, I did not calculate, but it's connected to the so-called dynamic viscosity. When you're passing by with in a fluctuating gravitational environment as a, let's say, satellite, then you feel a drag. This can be, I don't know, this is simply thermodynamics. We observe that this is a interesting exact solution and try to test it. What does it? It is coupled, so that the trace of that is coupled to that. And if I eliminate, in case of, by the way, internal variables, it's the usual trick is we eliminate them because we don't know exact meaning in, for example, what is the structure of this desk, which is not very much interested, or rock. Therefore, we eliminate them, and therefore we obtain a higher order derivatives, time or space derivatives, like in case of, for example, in the moment series expansion several times in kinetic theory. So this is, for example, one kind of deviation that we are investigating and whether could give good results. And now I really thank you for the attention. That's the end of the talk. Yeah. Galilean fluids. Yep. No, the whole, yeah, that I mentioned, I tried to group what I wanted to say in this way because really, I don't know, that's a short answer. So relativistic fluids are problematic from this, I mean, not straightforward to apply thermodynamics to relativistic fluids. What people can do, that Eckhart did actually, in a sense. This finer analysis shows you some possibilities how to do. The main point is that in non-relativistic fluids, there is a absolute time. And in relativistic fluids, it is not clear what is moving. You need a space and time separation for thermodynamics in this, at least in this form. It was not accidental to use only the gradients as the variables. If time derivatives are not only suspicious from an objectivity point of view, I mean they transform with the observer, but also, by the way, that's why Schrödinger equation is not Galilean invariant without any further ado. So it's a tricky thing, but you need the space and time separation. And in case of relativistic fluids, what we have tried, and I have tried, is for the Eckhart instability, it is clear that one part of the business is that Q, I mean the time space-like and space-time-like part of the energy momentum has very different physical meaning. One is the energy flux, which looks like dissipative. Another is the momentum density, which is not dissipative, but they must be equal. Therefore, one point is that maybe thermodynamics can differentiate, I mean, separate that. That's why, for example, introducing the energy momentum density vector as a, let's say, variable of the entropy density. So not only energy density as then the energy momentum, then you get this kind of separation, but it is not, not enough. What is, you know, in this case, so S will depend on E nu. And of course, if you derive by, so you get the temperature as a vector, just a derivative of, so you get beta u equals, okay. And that's, the question is that this beta, I mean, this beta vector, it is a 4 vector, temperature vector, whether we may fix, for example, the frame to that vector. This is the so-called beta frame, you know. And that seems to be a good candidate for relativistic fluids to make this time space-like separation. Neither Eckhart nor Landau-Lifshitz is somehow not suitable. And, but it is over-determined, actually. That I will show you the details if you want. This is an, when I encountered this problem, or we encountered this problem, then we turned back to the non-relativistic case to understand, maybe we can learn something in detail. Yeah. Yeah. Yes, I'm sure there was a logical connection. So how does this address the instability? I wanted to put the Korteweg instability, which is not well known, in a broader context to elevate a little bit. And that was one point. Another point is that if you, let's say, try to think about that, why and in what sense could be the second law, first principle, I mean, why does it, how was it connected to the Schrödinger equation, then you need a reason somehow. And the only reason I can imagine, only, let's say, a little bit more general view, is that it is related really to the stability of matter in a deep sense and several hierarchical level. And therefore, a very good benchmark of all these arguments is how could we deal with that kind of instabilities with the help of thermodynamics. So how could we connect dynamic stability to thermodynamic stability, a little bit extending the thermodynamic framework, for example, to gradient systems in this way. So this is, but it's really, so maybe this is a background. Also, a less known question about so thermodynamic stability is a concavity of the entropy. So I assume some variables, and I assume also this is a concave function, which is material fixes. And we have good reasons why that form and how, and of course, background. But if you, how to say, and normally we fix it, and so we have the normal thermodynamics is based on quasi-static and that kind of mysterious, very obscure process concept without time, which is really, in reality, it works because power stations are working, so it's just evidently. However, it is not, so at that level, so at the level of homogeneous thermodynamic bodies, it is not really the thermodynamics. I mean, there is no dynamic stability on this very obscure process stability. And it is an old problem of continuum physics. So the old guys, I mean, the big guys of continuum thermodynamics were really struggling with that, how to connect continuum stability questions to the classical thermodynamics. Of course, we can introduce entropy balance, but whether is it influences stability or not. And therefore, one may introduce, anyway, a dynamic version of homogeneous bodies, ordinary differential equations. I characterize the temperature of the room as a time-dependent temperature, for example. It's an approximation, of course, but still, the thermodynamic formalism should work. And actually, if the room temperature cools down because outside is cooler, then we have a differential equation of that. The question is how to connect this well-known exponential cooling curve, Newtonian cooling, with the mechanical part. And that's a tricky thing, but what I wanted to say that it can be done. One can find a system of differential equations, and one can, let's say, characterize open system, these simply open system families with thermodynamic framework where the entropy of the body and the environment together will be a Lyapunov function of the of the body itself. So this is so there is an analogous characterization of dynamic stability in case of ordinary thermodynamics between the continuum and between the usually accepted one. Yeah. Yes, but you need the transport. I mean, characterized the heat exchange coefficients should be non-negative as well. So the heat conduction, that's analogous to heat conduction. Also, friction. You get, let's say, expressions for the viscosity in this general sense. And the problematic aspect, why is it to connect to the mechanics? Because mechanics has a second order differential equation, Newtonian one, and this kind of naive thermodynamics is somehow always relaxation. And that to put together these two things is the trick. Yep. 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 Then go via hierarchy of scales, let's say time scales, length scales. Yes. The appropriate would be less and less forgetful about the collective. Yes, 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 yes. Time scales, length scale. So one step back would be hydro variables, hydro length scales. But then you can go down to the individual particle. So, yes. I mean, technically it may be difficult, but I don't see any kind of conceptual tension of the thermodynamics and dynamics. But the system remembers still things which were existed on the previous step. Then you go many steps down, it forgets. Right? So okay, two things. Conceptually, yes, I don't know, by the way, that the stability of these Korteweg fluids, how does it really relate it to single particle Schrödinger equation, which is somehow a kind of extension of, they are more kind of dissipative mechanisms can be written based on fluids than we can put with the Lindblad equation, for example. I don't know the relation, just I think that's a little bit different. Regarding the time dependent, I mean thermostatics or thermodynamics, one point I would like to mention, which is really could be conceptually problematic. So we usually put the Gibbs relation in this way. Let's say this is the where normal thermodynamics courses start. And if you want to introduce a differential equation like cooling law of Newton, then we get that E dot, this is a time derivative, room temperature. I mean, it's okay, this energy of the room, let's say heat capacity times temperature minus alpha times T minus T0, let me say. Yes, if the external temperature is higher, then the internal temperature increasing. Therefore, it is one can attempt, of course, this is, okay, differentials are not important. I mean, S is, let's say, a simple function of E and V. And therefore, so this, let's substitute with time derivative. And of course, this is a kind of power. And then we usually introduce the first law, like, let's say, some delta Q, or I don't know, this different, university to university is different. So the heat exchange plus work exchange. So sorry for the notation if you don't, so, but it's fine. And we take it equal. But this one, as it is clear, depends on the environment. Entropy depends on the body. I mean, only on the what kind of gas we have here inside. And how could it be equal? And it's very clear, by the way, if I introduce a kind of dynamical Lyapunov function-based argument that, yes, I can put this equality, let's just neglecting the details, of course. And however, this should be the differential along the the time derivative along the differential equation. So I need to introduce the particular, let's say, hidden dynamical information, and then it is really mathematically will be correct. So I don't know whether is it clear. So if I assume a differential equations for let's say the heat exchange here, and then that will be the let's say d Es times E dot, but not E dot anymore, but this differential. It's a constrained inequality in the sense what I've no constrained equality, or so this is valid along the process. So this is absolutely hidden in normal thermodynamics. No, but very simple and actually beautiful to see. I know, by the way, I don't know whether anybody uses it. It's very, how to say, in a corner of the literature. By the way, one additional sentence. So whether, okay, the second law is the first principle. Is it, and what I want to emphasize, does not contradict that it's also an emergent principle. But of course, it doesn't deny that if I know the structure of the system, then I can put into the information, and then the structure may fulfill. I mean, this should go along the second law. What one can get with this, let's say, abstract use without without using any microscopic or mesoscopic information is that I can get what is independent of the microstructure. So, for example, that's why I say that this simple classical holographic property seems to be quite general, because it's any. Okay, in this particular model it's true, but it should be valid for any several different kind of microscopic information or mesoscopic information. Yep. Thank you.
And how this is related to the divergence time? Do you think that
yeah. Not. It is really first order simple, no second order. So this is a one component fluid, Navier-Stokes. It is connected to the fact that for non-relativist, so to prove non-relativity, so the moment series expansion, you get phenological equations from the moment series expansion, and you can, let's say, close it with the help of the so-called main field. Therefore, you change from the extensive to intensive quantities. This is the trick of Tommaso Ruggeri. Then you also need to consider the covariant form of the equation. So these transformation rules that I mentioned here, they extensively, so they are used in the proof of the of the symmetric hyperbolicity, of the nonlinear symmetric hyperbolicity of the non-relativistic kinetic theory moments. This is the so-called rational extended thermodynamics. And then they, let's say, introduced the first divergence type theory, which is very complicated because of this background, based on this idea for the relativistic case. And then that was generalized by Lindblom and Garrosh. It is not. This is just. This is the transformation rules only, but for example, this is important when you introduce heat flux. I mean the proper transformation for the heat, proper variable transformation for the heat flux as a variable, because in that case it's not a constitutive quantity but a field quantity. So this is the connection. That's in the book of Müller and Ruggieri. It is very clearly written that. Yeah. Thank you. Yeah, exactly.